I'm down.
Okay, let's take a minute and see if we can find this integral. So this is like we have z equals 60xy. We have this surface, and we want to integrate this surface with this base. In other words, over this region, where these are just lines. You got this little diamond here. So you want to integrate over this region. Okay? So take a minute and try to do that. Find this integral over that region. Actually, let me make a change here. Let me make this 2 here. Let me just make this a 2. That's what I had intended. I'd intended for this to be a 2. Yeah, so let's use that. Now let's think about this. You notice here we've got 4 sets of lines. Okay? I'll call this line 1. I'll call this one line 2, line 3, and line 4. Okay? Now, let's think about the equations. So, of those lines, because remember, we're going to have to integrate from one line to the other. We're going to have to maneuver over this region. So we need to be able to go, like y is going to need to go from line 1 to line 2, or x is going to need to go from line 1 to line 4. X is going to need to go from line 1 to line 2, right? So we're either going to fix x and have y go from like line 1 to line 4, or fix y and have x go from line 1 to line 2 here. Okay? So we're thinking about that. We're thinking about how are we going to go through this interval. Now, if you look at line 1, that's going to be y equals negative x plus 1, right? That's the formula for that line. Now, what about line 4? What would line 4 be?
Y equals x plus 1.
Yeah, y equals x plus 1, definitely. Okay, so there's a hint. Now, you're going to need to do that for L2 and L3 as well. Now, I'll go ahead and look at L2. L2 is going to be, it looks like it's going to be x minus 3. Is that right? Is it minus 3?
Yes.
Yep. Okay.
No.
Minus 2?
It'd be minus 1.
Minus 1?
Minus 1. Sorry.
Minus 1? I don't know where I got that. Minus. Okay. So let's see if it works out. If I put in a, so we're looking at line 2. If I put in a 2 in, well, that won't work, will it? Let's see here. We've got a slope here of 1, right?
And it's intersecting the y-axis at negative 1.
So we've got x minus 1, right?
Yes.
So, yeah, that'll work. That'll work. Now, what about L3?
Negative x plus 3.
Okay. Yeah, that's where I think I was thinking about this one when I did the plus 3. Yeah. So if we go through the process, finding slope and y-intercept and all that, we would get these lines. So now this gives us a way to define line 1, line 2, line 3, and line 4, which means now we can integrate. We can integrate from one line to the next. If I want to integrate from line 1 to line 4, no worries. If I'm integrating with respect to y, I'm going to go negative x plus 1 all the way to x plus 1. See? Okay, so continue to work on that. Get your integral set up. Now, there's going to be 2 sets of doubles. There has to be 2 sets of doubles here. So just keep going. Try to set them up. Okay, let me move along here. So I've got 2 sets of integrals. I've got 60 xy in here. And now, I think what I'm going to do is I'm going to integrate with respect to, I guess I'll integrate with respect to y. Because then I could just say, well, I'm going from x plus 1 all the way to negative x plus 1. Okay? So you give me x, and I'll do that, but be careful because that only works to this point right here. So x is going to go from 0 to 1. See that? See? So you give me x, because once I pass by this, then I've got something else. I've got 0 to 1, and now I'm going to go from L2 to L3. And this time, whoops, so this is what y does, and then x is going to go from 1 to 2. Put 0 to 1 at first. There we go.
On the first one,
Are those not backwards?
are the bounds not backwards?
The bounds are backwards.
That's what I think.
Well, x is going to go from 1 to 2.
No, the first double integral.
Oh, the first one?
The second integral on the first double integral. The y bounds.
The y bounds?
Yeah, isn't it? Yeah, are they flipped?
Let's see here. I'm going to go from...
They should be flipped.
oh, yeah. The way I was looking at it. I got you. I was looking at it. Yeah, you're right. So this is going to be negative x plus 1 to x plus 1. Yeah, that's it. Perfect. Thank you. Yeah, there it goes. I'm going to make excuses for myself. I was looking at the order here. Wasn't my fault. Okay, any questions? Now look, we could go ahead and work through both of those and get the right answer. We would work through both of those and get the right answer. But what we want to do is we want to explore something different. In other words, what I would like to do, I don't really like this region that I'm dealing with here. So what I want to do is I want to convert it to a simpler region where I can maybe solve this problem with one set of double integrals instead of two sets of double integrals, because I got other things to do. Now, I want to just have you hearken back to when you were much younger. And you had maybe an integral like this. And let's see here, maybe x goes from 0 to, the square root of 3. Let's think about that integral there. And this integral might give you fits the way it is. However, you could do this. You could say, I'm going to let x be tangent of u. That's what I'm going to do. I'm going to let x be tangent of u. Now this here is we're doing a transformation. We're changing this integral to something else. Okay? Something else. Now, if I do that, notice what I've got to do. I've got to say, okay, dx is equal to secant squared u du. Okay, so this is one of the things I have to do. When I do this transformation, I can't just say, oh, I'm going to replace x with tangent. I can't do that. There's something else I have to do. So this is going to be the square root of 1 plus tangent squared u. And then I have to do secant squared u du. I have to do that. That's one of the things I have to do. Okay, that's not the only thing I have to do, because now I have this situation. I have that x goes from 0 to the square root of 3. But I want to say, okay, now my integral now is in terms of u. So what does u do? Well, u is going to be, really, if you think about it, arctan of x. So u is going to equal arctan of square root of 3, which is going to be pi over 3. And then arctan of 0, which is 0. So our integral up here is going to be 0 to pi over 3. So we've transformed that integral. We did two different things. We had to do something here, and then we had to do something to the bounds as well. So we did some substitution. Now, this was a particular way I looked at this. We could do this for, just in general. We could have the integral from a to b of f of x. And we could do a transformation where we say x is equal to g of u. And then dx is equal to g prime of u du, like that. And then we could change the bounds. And what we would find is this is going to be the integral of f of g of u, and then g prime of u du. And of course, I guess we would say g inverse of a, g inverse of b. Okay. So in other words, we could be more general. But in other words, it's the substitution method. And this is not usually how we did the substitution method. Usually with the substitution method, we would say, let u equal something. Okay? We'd say, okay, let u equal something, then du equal, But we've also, when we did trig substitutions, we had things like this. Okay, any questions? So over here on this one, we get the integral of secant cubed. And we know how to find that integral. Okay, any questions about that? Now, with that in mind, this is just something that we learned in Cal 1. Let's go back to that problem we were just working on. And I've got this thing. Okay, so this right here is a 1, 2. This is 2, 1. This is 1, 0. And this is 0, 1. Yeah. Okay. This is xy. Now, I want to do this. I want to make this substitution. I'm going to say, well, let's let x be 1/2 of u plus v. Okay? In other words, it's not just in terms of u, it's in terms of v. And I'm going to say let y be negative 1/2 u minus v. Let me just do this. And don't fret over where I came up with that. This is just a transformation that I'm going to use that's going to make things easier. Okay? I just want to show you how it works. Okay. So we've got this transformation. So just like before I said, we'll let x equal tangent u. Now I'm saying we'll let x be 1/2 u plus v, y equals negative 1/2 u minus v. Okay? Now, I've got this transformation as it is right here, and I want to solve in terms of u and solve in terms of v. So in other words, I want to have x equals, y equals, but I also want to have u equals and v equals. I want to know what those are as well. Okay, so here's what I'm going to do. I'm going to take, for example, I'm going to take the x plus y. Okay, let's just do this. X plus y, and let's see what that's going to be. That's going to be 1/2 u plus 1/2 v plus 1/2 u
minus 1/2 u.
Minus, well, let's see here. I'm doing the minus. So let's see here what I've got. I've got plus Let's see.
X plus Y, shouldn't it still retain the,
Oh, yeah, that's right. In my mind, I think I was doing the, I was doing the minus in my mind. So look, we've got 1/2 u plus, minus 1/2 u. And then we have 1/2 v plus 1/2 v, right? Yeah, there it goes. Okay, does everybody see that? In other words, if I just add x and y, look what I get. I get this. I get x plus y is equal to v. There. So now I know what v is in terms of x and y. Now, let me do this. So let me mark that, and now I'm going to go back and do x minus y. Okay? So I get 1/2 u plus v minus a negative 1/2 u minus v. Let's see what this turns out to be. Okay? So here we go. We got x minus y equals 1/2 u plus 1/2 v plus 1/2 u minus 1/2 v. And now we get this. We get u equals x minus y. Okay. Now, you may not know where I'm going with this. I'm sure you probably don't. But the thing is, I've got this region right here, and I'm just going to do this transformation. I've got x equals 1/2 u plus v, y equals negative 1/2 u minus v. And what I'm trying to do is go away from this xy axis to the uv axis with that transformation. Let me show you how it works. Okay, so now I've got over here, I've got the uv axis. And I've got some points here. I've got these points. I've got 0, 1. I've got 1, 0. I've got 2, 1. And what, 1, 2? Are these my points? Okay. Now, I want to get a u, and I want to get a v. So I'm trying to get the corresponding points on the uv axis. Okay. Now, remember the u is x minus y, and the v, what was it, x plus y? Okay, there's what I had. Now, let's see if we can see what u is, what u are. Now, what u is. So, now remember, this is exactly the way it goes when we're changing bounds of integration in single variable. But now we got two things. So look, when x is 0 and y is 1, this coordinate is negative 1. And this one would be 1. So we've got this point. We've got this point, negative 1, 1. Okay. Now, if x, so now this one, if x is 1 and y is 0, we've got u is 1. And then over here, this is 1. So we've got this point, 1, 1. And I think what I'm going to do, the way I've drawn this is not going to work out too well. I should have planned ahead. I'll redraw it here in a minute. Okay, now let's see what we've got. When x is 2 and y is 1, we've got 1. And over here we've got 3. Then down here we've got 1 minus 2, that's negative 1. 1 and 2, that's 3. Okay, so what is this? This is 1, 3, and this is negative 1, 3. Okay, there we go. See, so what I've done is I've transformed those points. Now, let's see what this looks like. Let's plot these points. I've got negative 1, 1. It's about right there. I've got 1, 1. Right here. I've got 1, 3. And negative 1, 3. Now look what I've got. There is my region that I'm going to integrate. See, it's no longer a situation where I'm going to have a double integral. I'm going to have, okay, so here is 1, 1. Here is negative 1, 1. Here is 1, 3. And negative 1, 3. And I've got this UV. Okay, does everybody see that? In other words, in Cal 1, when you did substitution, you just had to say, okay, x goes from A to B. Well, what does u go to? Well, you had to calculate that. That's all we're doing here, except with 2 dimensions, it's more challenging. Okay, now let's see what we've got here. We've got 60. Let's go back to our integral. 60. We've got double integral, and we've got x and y. Now notice that x is 1/2 u plus v. Y is negative 1/2. What's it? Negative 1/2 u minus v. Okay. See, instead of 60xy, there's what I have. Now, I can do my bounds of integration. It really doesn't matter which one you choose first. I think I'll just do, dx. dx over here is going to go from negative 1 to 1, and dy is going to go from 1 to 3. See, just set my integration that way. So I'm going to integrate with respect to v first, it looks like. Okay. Now, remember what I said. I said, when you do these, I guess I did it. I guess I wrote it over here. I said, when you do these, you've got this thing. Okay? There's something that you can't just substitute in and change the bounds. There's going to be something that is going to be multiplied here. Now, this is the Jacobian for this 2 dimensions. Now, let me just give you the Jacobian, how we're going to calculate the Jacobian. Okay. The Jacobian is written this way.
Is that partial?
Yeah, it's an operator. But let me show you what this means. This is the Jacobian. And what you're going to use, you're going to do the absolute value of it. So it's going to be the absolute value. Okay? So it's going to go like this. It's going to go partial of x with respect to u. Partial of x with respect to v. Okay? Partial of y with respect to u. And partial y with respect to v. You're going to use the absolute value of it. Okay? Whatever that number comes out to be, you're going to use the positive. Okay? So let's look here and see, well, what is the partial with respect to u? The partial with respect to u, the partial of x with respect to u is 1/2. See that? Partial with respect to down here. Okay, so both of these are going to be 1/2. Now, the partial with respect to y of u is going to be negative 1/2. And the partial with respect to v is going to be positive 1/2. In other words, we're kind of using this determinate form so that we can easily remember how this works. So this is going to be 1/4 minus a negative 1/4, which is 1/2. Okay. That right there is the missing piece that goes right there. That's what has to go there. Okay. And then, so what do? We did the dv, du. Yeah, and there is what we use to find that integral. So we've transformed. So we've gone from the xy plane to the uv plane, and we've gone from this diamond-shaped thing here, where we use two integrals, down here to where we can use one set of, we use two doubles, and here we can just use one set of doubles. Okay. Now, so this thing of the transformations, you could have something like this. You could have x squared plus 4y squared equals 1. Okay? And we could say, well, I want x to be u plus, let's see here. Let me see. I forgot how I wrote that out. Let me see here. I had to transfer. X plus, oh yeah, okay, I forgot what I was going to. So this is going to be, let's suppose that u equals x plus 2y, and v is equal to x minus 2y. Let's suppose we have something like that. And we want to make a transformation. In other words, think about how this looks. What is that? That's an ellipse, right? It's an ellipse, and if we were to sketch that, we go from negative 1 to 1, and then up here, negative 1/2 to 1/2, so it would look like this. This is what that graph would look like. Okay, does everybody see that? In other words, we have something elliptical. Now, let's just see a transformation that could happen. We could say u plus v. Well, u plus v is going to be, what, 2x. So this means that x is equal to u plus v over 2. We could also say u minus v. Okay? U minus v, you're going to have, let's see here, x plus 2x. So this is going to be 4y, isn't it? And that would give you y is equal to u minus v over 4. See that? This is just to show you how these transformations can work. Okay. Now, I'm going to go back to my original, x squared plus 4y squared equals 1. And let's see what we get. Here's x squared plus 4y squared equals 1. Now let me work this out, because what we're trying to do is see, okay, what is this going to transform to in the UV plane? Okay, so here I go. I've got u squared plus 2uv plus v squared over 2 plus, let's see what this is going to be. This is going to be, Oh, this is 4 down here, isn't it?
Yes.
Okay, over here, you're going to have 1/4 as well. And this is going to be u squared minus 2uv plus v squared equals 1. Now I'll just multiply through by 4, and I'll get this. U squared plus 2uv plus v squared plus u squared minus 2uv plus v squared. Okay. Now, equals 4. Okay. Now, let's see what this looks like. This is 2u squared plus 2v squared equals 4. See, because the 2uv's cancel. Divide by 2, and look what you get. U squared plus v squared equals 2. Ah, that's a circle of radius 2. So in the UV plane, you get a nice circle of radius 2. Or square root of 2. You get a circle of square root of 2. So there's an example of a transformation. Okay. Now, what I want to do is kind of walk you through in your book. If you'll look at number 15 on page 1032. So on page 1032, we want to look at number 15. And what you're going to do is you're going to use the transformation that they gave you. Notice they gave you the graph up there. So you'll just pattern your work after what I did. And I'll wait, and then I'll lag behind a little bit and work through part of it. You know, I'll work through it after you've had a chance to look at it. Okay, we're running out of time, so I want to just go through here. Notice how I set it up. I've got my region here. I've got my transformation. I know what my x coordinates and my y coordinates are. I know what the xy coordinates are. I know the ordered pairs. So I wrote those down. What I need to do is figure out what the UV coordinates are. So I need to know how to find that. I need to be able to, you give me the x and the y, and I'll tell you what the u is. Okay? You give me the x and y, I'll tell you what the v is. So I do that by saying, okay, let me see if I can get a relationship here. X plus y is going to equal u. You know, if you just add those, you find that u equals x plus y. Now, if you subtract, let's see if I do y, x minus y. Well, then I get v is equal to x minus y. Now, let's see what I can do then. For this point, u, okay, and let me spell this out a little more. Okay, u is going to equal x plus y. V is going to equal x minus y. And then I've got the uv. Okay, so here I've got u is equal to -1. And y is equal to +1. See? Because x is 0 minus a -1. So I've got this point. I've got -1, 1. So that's going to be, if you go up here on the uv axis, -1, 1, it's going to be about right there. Then I can do the same thing for the 1, 0. I've got y, I've got u is 1, and v is 1. So I've got the point 1, 1. Okay. So that's over here, about. Okay. Everybody see that? Now, 0, 1. So once again, that's 1. and then negative 1. Okay? So 1, negative 1 down here. Okay? And then finally, the grand finale, I've got negative 1, 0, so this is going to be, well, negative 1. So this is negative 1, negative 1. Okay, so look at this. There. So I've got, now this is my region. Okay? This is my region. So things have changed a little bit. Now, I'm going to integrate over that, but I need the Jacobian. So the Jacobian is going to equal partial x with respect to u, partial x with respect to v, partial y with respect to u, partial y with respect to v. I'm going to get 1/2. Well, heck, I'm set now. I'm going to go 4, and I've got my Jacobian, and I've got x squared, which is 1/2 u plus v squared plus 1/2 u minus v squared times 1/2 du dv. And u is going to go from, let's see here, -1 to 1. And this one goes from -1 to 1. So there it is. That's what you would integrate.
And since there's symmetry, could you multiply it by 2 twice and go from 0 to 1?
You got to be careful when you're using symmetry because what the top is doing. In other words, you got to be sure, you got to be certain of your symmetry.
Oh, okay.
Any questions about that?